Hi, and thanks so much for clicking on this video. And welcome to Integral of Symmetry. Integral of Symmetry is a new method in order to calculate any primitive of any function in any dimensional space. And in this second video, we are going to calculate our first primitive in three-dimensional space. And we are going talking about the scalar function and identity function in our three-dimensional space. That is f ds y equal z equal s plus y. And it has the following representation in the right hand three-dimensional coordinate system, which is a plane, an inclined plane that passing for the horizon, and we prefer illustrated that function with this construction. As you can say, this is the first attempt into the coordinate system, and our function is something like this. It's represented by this surface, by this plane, and you can imagine that plane extending in all directions with the same slope. Only we represent the positive part of the three-dimensional coordinate system of the first attempt. Now, the method that we are going to use in order to calculate that primitive is the same method that we used in the last video when we calculated the primitive of the identity function in two-dimensional space. It was fds equal s, fds equal s, and we calculated that primitive and the primitive of any power of this function. We are going to say the same in this video using the same procedure that we used in this last video. And we first began studying what is the symmetry of that function, of that representative plane. What is the symmetry of that figure, of that plane into the coordinate system, just like we study the symmetry of the triangle who was represented the linear function, the identity function, into the square. It was represent the Cartesian coordinate system, and we find that the symmetry is 2. But now we want to calculate it. We want to study what is the symmetry of this prism. This prism is representative of that surface, because this surface, this face, has the same surface of the identity function, as you can see in this construction. Now we can calculate it, we can estimate what is the symmetry of this prism into the coordinate system. Remember, the way that we are going to follow to calculate it, the primitive, is by knowing what is the volume under that surface. The volume under that surface, just like the area on the line of the identity function, it was the primitive. Now the volume under this surface is going to be representative of the primitive of that function. For that, we are going to study the symmetry of this prism. We represent the identity function into the cube, which is representing the coordinate system. Just like we study the the symmetry of the triangle into the square representative the identity function and the square representative the Cartesian coordinate system. Now, in fact, we cannot see what is the symmetry of this prism into the cube, just like we could see the symmetry of that triangle into the square. But we know by the solid figure that the volume of this prism is exactly the volume of this cube divided by 3. But we are not to say that anymore. In the vocabulary of the integral of symmetry, we say that the volume of the prism is going to be the volume of the cube divided by the symmetry. Now we can write our primitive in this form: integral of s plus y, we use bracket, dsy, this is a new notation, is going to be the volume of the cube divided by the symmetry of the identity function. And this symmetry we know is 3. And the volume of the cube, if we draw a little cube here, if we try to draw a little cube in this coordinate system, we have the following dimension of that cube. We have that dimension of that cube. This cube had width white, this is white, our y axis, this is width, this is length is s, our s axis, and the height is z in our z axis, and z is equal s plus y. The volume of the cube obviously is the multiply of his side, and we have s times y times z, but z is s plus y, and we have again s times y times s plus y. But now again s and y are the same that z, because we are talking about the cube and have the same edge, and we have them s is equal s plus y is equal s plus y, and times s plus y, and we have finally s plus y to 3 divided by the symmetry, which is 3, plus a some constant of integration. Now, in this point, we apply the same procedure in the last video when we define the hypothesis of the integral of symmetry. That hypothesis allows us to calculate any primitive of any power of the identity function. That hypothesis states when we study the symmetry of any power of the identity function, we know that this symmetry increases the same quantity that the power increase. We are talking about this. If we want to calculate it now, another function f ds y equal z equal s plus y to m, and this integral, this primitive, is going to be the same volume of the cube. Now it's not maybe not cube, maybe a parallel pipe, divided by the new symmetry. That new symmetry we call S prime. And this symmetry is going to be the same, the former symmetry 3 plus the increment of the symmetry of the identity function. 3 is the symmetry of the identity function, and we add the increment of the symmetry by the power. We see the same increment of the power m to 1, and we have the increment is going to be m minus 1. M minus 1, 1 from the identity function, the power of that function is 1, and the power of that function is m, and the increment is going to be m minus 1. And the length is s, the width is y, and the height is no longer s plus y, now is s plus y to m. And we put s plus y to m. And finally we have the following formula: s times y times s plus y divided by 3 minus 1, which is 2, and we have m plus 2. Then s and y are the same again, because we are talking about the cube, and the cube remain in this former value s plus y, and we have s plus y, we substitute s by s plus y and y by s plus y 2 times s plus y to m divided m plus 2, and we have s plus y to m plus 2 divided m plus 2, and some constant of integration. Well, this is our first primitive, this is our first general formula of any power of the identity function, just like the formula of the classical calculus that we inherit from Newton and Leibniz 300 years ago. You remember, integral of s to m ds equal s to m plus 1 divided by m plus 1. This is similar to our new formula, and in the next video we are going to use, and you will be a witness of the amazing power of this formula to calculate volume in the three-dimensional space with a simple substitution, just like primitive of the two-dimensional space when we calculate the area. Thank you so much. I hope see you in the next video.